Recording in progress.
So is my screen visible to you?
Visible, sir. Slightly make it bigger, sir.
Yeah,
Better, sir.
I'm just trying to zoom in.
It's the bottom side. Yes, sir. Thank you.
Okay. So
Correct.
this is visible to you, right?
Yes, sir.
Okay. So this is the question. Maybe it is too big for me to, maybe page width will be better. Okay. So this is the question, the first question on temperature measurement. It says that the time constant of a first order thermal system is given as 0.5 minute. The uncertainty in the value of the time constant is given by plus minus 0.01 minute. The initial temperature excess of the system over and above the ambient temperature is 45 degrees centigrade. And you are asked to determine the system temperature excess and its uncertainty at the end of 50 seconds from the start. Okay. So this is a first order thermal system, and we had studied in the class. In fact, if I go to the slides, okay, I have to change slide, but I will write down here. So we had studied something like this, T of time minus temperature of the ambient divided by temperature at T equal to 0 minus T infinity as e to the power minus T over tau. This is something that we had derived in the class for a first order system, thermal system. So this is the temperature at any time point. This is the ambient temperature which is fixed. This is the initial temperature of the system, maybe a thermocouple, for example, at T equal to 0. And this is again the ambient temperature. This is time, and this is your time constant. Okay. So this Tt over T infinity is called the excess temperature. That means the temperature of the system at any time T over and above the ambient temperature. Similarly, this is the excess initial temperature, that is T0 minus the ambient temperature. That is equal to e to the power minus T. So this is written in this form here. Okay. This excess temperature is Tt and excess temperature, initial temperature is T0, which is equal to e to the power minus T over tau. Okay. Now, talking about this question, the time constant is given. The time constant of a first order thermal system is 0.55 minute. So your tau is given, that is 0.55 minute, which will be equal to 0.55 into 60, that is equal to 33 seconds. So it is always advisable to work in SI units, so you convert a minute into second. Then you are asked to determine the system temperature excess and of course its uncertainty at the end of 50 seconds from the start. That means you are supposed to find temperature at 50 seconds. So temperature at 50 seconds from this formula here, the excess temperature at 50 degrees centigrade will be equal to temperature at T equal to temperature at 50 seconds will be equal to temperature at T equal to 0 times e to the power minus 50 over tau. Tau is basically 33 seconds. So The initial temperature excess of the system over and above the ambient is 45 degrees centigrade. So that means your T0 is 45 degrees centigrade. So 45 into e to the power minus 50 over 33. That gives you 9.89 degrees centigrade. Okay. So this is the question asked, what is the temperature at the end of 50 seconds? Okay, so that question you had you have answered. But you also have to find the uncertainty. Okay. So now the uncertainty in the temperature at 50 degrees centigrade would depend on the uncertainty in the time constant, because uncertainty in the time constant is given here. Okay. So in this case, we are talking about propagation of uncertainty. That means the uncertainty in the time constant will reflect in the uncertainty in the temperature at the end of 50 seconds, right? So first, we write down the uncertainty in the time constant in terms of delta t, which is plus minus 0.1 minute. Okay, that is 0.1 into 60. That is point plus minus sorry, this is 0.01, not 0.1. It will be 0.01 into 60, that is plus minus 0.6 seconds. Okay. So that is the uncertainty in the time constant. So how do we know how the temperature uncertainty will change? We need to use the propagation uncertainty formula. That means we need to find out how the temperature changes with the time constant, dou T over dou tau. Now, what is the temperature expression? So this is dou over dou tau into the temperature expression is T0 e to the power minus T over tau. T0 is a constant, so it can go out of the bracket. Then e to the power minus T over tau into T over tau square. Okay. This is the derivative of this term. Okay. So now if you substitute the values, T0 is 45 degree centigrade. Then this is e to the power minus 50 over 33 into T is 50 seconds divided by 33 square. And that will give you 0.454 degrees centigrade over second. So this is the how temperature changes with respect to the time constant. So if you know the derivative, then you can use the propagation of uncertainty formula to find out what is the uncertainty in the temperature. Okay, so the uncertainty in the temperature delta T at time t equal to 50 seconds is going to be plus minus dou T or dou tau into the uncertainty in the time constant. Okay, so we wrote, I think the symbol that we wrote was u delta T will be equal to dou T over dou tau plus minus u delta T. So same thing we're writing here. So that is basically plus minus. This gradient is 0.454. And the uncertainty in the time constant is 0.6 seconds. So when you calculate, you get this as 0.272 degrees centigrade. This is the uncertainty in the estimated excess temperature at T equal to 50 seconds.
Sir, the T by tau square, we are multiplying with the whole term, right?
So you have basically dou T over dou tau into the tau whole square, then square root, right? That is what the formula is, isn't it? If you have other dependency, they will also come as square term. But here only one term is there. So you square it and square root it. So it is basically the same thing. Okay. Is it clear?
Yes, sir. Yes, sir.
Okay. If you are done with this question, then I will move on to the next question.
Sir, can you just slightly scroll up? Sorry. Just 1 second. Just 1 second. Yeah, okay, sir. Thank you. Please keep your microphone muted. I hear some noise. So this is the second question. A K-type thermocouple is used as shown in the figure here. I will show you the figure. Sorry, I have not the figure here. Let me draw it for you. Without a reference junction. Okay, so this is the figure that I wanted to show you. You have a measuring junction. This is the voltmeter. This is the positive wire. This is the negative wire. This is the measuring junction. Okay. So you have two thermocouple wires which have a measuring junction, but there is no reference junction. Okay, it is directly connected to the voltmeter. The terminals of the voltmeter are at room temperature 30 degrees centigrade, while the measuring junction is at 100 degrees centigrade. So the measuring junction temperature is 100 degrees centigrade. The terminals here are at 30 degrees centigrade. Okay. Now you have to tell me what is the voltmeter reading. Okay. And what would have been the reading had it been connected with the reference junction at the ice point? That means if you had a connection, something like this. So this is the reference junction. This is the measuring junction. If you had a reference junction at ice point 0 degrees centigrade, this is at 100 degrees centigrade, what would have been the output here? So these two cases, we have to know the output. So first, let us talk about the case on the left. That means without any reference junction. So if you do not have any reference junction, the system would automatically take this as the reference junction, which is at 30 degrees centigrade. Okay. So the case on the left, your measuring junction is at temperature 100 degrees centigrade. The reference junction is at 30 degrees centigrade. Now you go to the thermocouple table, but these thermocouple tables are actually made with the reference junction at 0 degrees centigrade. That means for this table, the reference temperature is 0 degrees centigrade. So how do? You use the law of addition, temperature addition. So here you break this into two cases, where in one case the measuring junction is at 100 degrees centigrade, and the reference junction is at 0 degrees centigrade. In another case, the measuring junction is at 30 degrees centigrade and the reference junction is at 0 degrees centigrade. Then if you find out the output here and output here and then subtract, then you get the output, that is when the temperatures are 100 degree and 30 degree. So in the first case, when it is 100 degree and 0 degree, you can go to the table and you see that the output when it is 100 degrees centigrade is basically 4.096. Okay, as I said, this indicates the second digit. We have 100. Had it been 101, then you will use this temperature. Okay, so this is basically the next digit, that is 1, 2, 3, 4, etc. Okay, so for 100 degree it is 4.096. So that means the output here 4.
Whatever temperature I'm measuring, only I have to see on the left hand side, right? TM.
Yes, because the reference temperature is already fixed at 0 degrees centigrade. Okay, for
Okay,
this.
sir. Yeah.
So you read V1, which is 4.096 millivolt. Then you go to the second case where the measuring junction is at 30 degrees centigrade, but the reference junction is at 0 degrees centigrade. Okay, so there you go to the table again and you go to 30 degrees centigrade. So what is the temperature? What is the output? 1.203 millivolt. So the output here is 1.203 millivolt. Now the total output when you have this case will be basically subtraction of these two outputs, 4.096 minus 0.203, that will be 2.893 millivolt. So this is how you find out the output of a thermocouple circuit. And here in the case on the right, it is pretty simple. I mean, you have the measuring junction at 100 degree, reference junction is at 0 degree. So this is same as the case here. Your measuring junction is at 100 degree, your reference junction is at 0 degree. So you just read these values. That would be the output, that is 4.096. So the output here would be 4.096 millivolt. Okay.
Hello. Hello, sir.
Right. So,
Hello.
yes.
Sir, what if we have TR in negative temperature?
So, when the reference temperature is negative,
Yes, sir.
See, when you have the reference temperature negative, then you need to have a proper table where these values here, the measuring junction values, also should have negative values. Okay, because this table is at 0 degree centigrade, but the measuring junction is above 0 degree centigrade. But you need to see if there are tables available where the measuring junction is negative and the reference junction is 0, or vice versa. The measuring junction is 0 and the reference junction is negative. Okay, so you need to look for tables if they are available. If they are available, then you can do.
Okay. Thank you, sir.
Or what you can do is you can use the Seebeck formula that we had used, which relates the temperature difference with the voltage. But there are, if you remember, there are calibration constants. Okay, those calibration constants have to be known, then you can mathematically solve and get the output for a given temperature difference. Okay, so that is another approach. That's an alternative to using table. But again, those calibration constants have to be known for a specific thermocouple.
Understood, sir. Thank you.
And Professor, reverse also can be like calculated, like if that millivolt is given,
Yeah,
then we can calculate the temperature as well, right?
exactly. If I give you the output, then you have to maybe somehow you have to sometime maybe you have to interpolate and find out the temperature.
So the between the points is linear interpolation only, right, sir?
Yeah,
Okay, sir.
you
Thank
do
you
a
so much.
linear interpolation just for an approximation, and that works.
Right, sir. Thank you.
Okay, so this is the next question, and this is related to a resistance temperature detector. The a resistance temperature detector has the temperature coefficient, resistance temperature coefficient alpha as 0.005 per degree centigrade, and resistance at 20 degree centigrade is 500 ohm, and the dissipation constant of 30 milliwatt per degree centigrade. I think you remember what we talked. We talked about dissipation constant of a thermocouple of an RTD, because typically you use temperature correction for resistance, right, using this dissipation constant. And so that dissipation constant is given to be 30 milliwatt per degree centigrade at 20 degrees centigrade. This RTD is used in a bridge circuit, that means the Wheatstone bridge circuit, with R1 and R3 500 ohm, and R2 is a variable resistor used to null the bridge. Okay, so you have, let's say, R1, so you will have something like this. Supply voltage, and this is R1. This is R2. R3. This is R3 and this is R4. Okay. So this is basically your RTD. Okay. And R1 equal to R3, which is 500 ohm, and your R2 is basically a variable resistor. So if the supply voltage is 10 volt and the RTD is placed at in a bath at the ice point, okay, that means 0 degrees centigrade, find the value of R2 to null the bridge. That means no current should flow in the bridge. Okay, so let us revisit the question. An RTD has a temperature expansion coefficient alpha 20 at 0.005 per degree centigrade, and the resistance at 20 degrees centigrade is 500 ohm, and the dissipation constant PD is given, which is 30 milliwatt per degree centigrade at 20 degrees centigrade. The RTD, this RTD that we just spoke about, is used in a bridge circuit with R1 and R3 500 ohm, and R2 is basically a variable resistor that is used to make sure that there is no current that is flowing. If the supply voltage is 10 volt and the RTD is placed in a bath at the ice point, find the value of R2 to null the bridge. Okay, and take the effect of self-heating. That is where the dissipation constant comes into picture, right? As we discussed in the class, whenever there is self-heating, to take care of the corrections in the temperature because of the resistive heating effect, we talk about the dissipation constant. So here you know that the current that flows through the RTD can be written as, from the bridge itself, is the supply voltage Vs divided by R2 plus, let's say, R1, which is 500 ohm. So this is the current that would flow in the bridge circuit, given the battery supply voltage is some Vs, which is given as 10 volt. The heat dissipation in the RTD, because when there is a current flowing through the RTD, there will be an I square RT heating, the resistive heating. So the heat that is generated because of the heating in the RTD, so the heat generated in the RTD is basically I square into the resistance of the so here, when initially when R1 equal to R3, at null condition, it is given R1 equal to R3 at all conditions. At null condition, when R1 equal to R3, your R2 has to be equal to R4, that is the resistance of the RTD, right? Then only the resistance, the circuit will be balanced. Okay, so that means you can, the resistance of the RTD you can write as I square into R2. So this will be equal to the current through the circuit is basically Vs divided by R2 plus 500 square into R2. Okay, so this is basically the heat that is generated from the RTD. Okay. Now, what is the self-heating? When the current goes through this RTD, there is going to be self-heating. Then self-heating is going to give rise to a temperature rise above the ambient. So this temperature rise because of the self-heating effect is going to be the rate of heat generation divided by the dissipation constant PD. So you can see that this has a unit of watt, right? Or milliwatt. And this has a unit of milliwatt per degree centigrade. So that will give you the temperature rise. So Q dot is basically Vs divided by R2 plus 500 square into R2 divided by PD. This is the rise in temperature. Now this rise in temperature gives rise to a change in the resistance. Okay. Now what would be the change in resistance? So let's say the change in the resistance will be basically at the reference temperature into 1 minus alpha into delta T. Right? This is the formula. Resistance at the ice point condition, because when the resistance of RTD at ice point, basically R2, which we are trying to find, and this is the reference temperature where the alpha is given. So 20 degrees centigrade is the reference temperature here. So R20 into 1 minus alpha 20 into delta T. So now I can write R20, that is the reference temperature, 1 minus alpha 20. Now this delta T is basically this term. Instead of delta T, I will substitute this term. That is Vs divided by R2 plus 500 square into R2 over dissipation constant. So now I can substitute the values. R20 is 500, then into alpha is 0.005 into I have done a mistake. So this delta T that I wrote should be actually the reference temperature 20 minus the delta T, because we had R at a particular temperature T is basically the reference temperature into 1 minus alpha into T minus T naught. right? This is basically the formula. So when we write resistance at the reference temperature into 1 minus alpha into, it should be the difference between the reference temperature and that particular temperature delta T. Okay, so that is why this should have been, so this should be actually 20. Let me erase sometime. So this should have been 20 minus this term. Okay, so basically 1 minus, this is 0.005, then I have 20 minus 10 divided by R2 plus 500 square into R2 divided by dissipation constant, which is 30 milliwatts, so write in watts, so that will be 0.03. Okay, so this is the equation. So let me go through from the beginning what we actually did. So the question is saying that an RTD has the value of the temperature resistance coefficient at a reference value of 20 degree. Okay, is given as 0.005 degree centigrade. Resistance at the reference temperature of 20 degree is given. Dissipation constant at 20 degree is given. Everything is given about the RTD at a reference temperature of 20 degrees centigrade. Okay, so that is the information about the RTD that is given. Now the RTD is used in a Houston bridge circuit with R1 and R3 as 500 ohm, and the R2 is a resistor but whose resistance can be varied, and this can be varied to null the circuit, null the bridge. If the supply voltage is given 10 volt, the RTD is placed at ice point temperature 0 degree centigrade. When this is placed at 0 degree centigrade, what should be the value of R2 to null the bridge? Okay, so when there is current flowing through the circuit, you have basically a potential of Vs applied across the resistor of R2 plus 500. So the current that will be flowing through the circuit is basically I square into the resistance, which is R2. This is because when there is a null, then RTD resistance and R2 will be the same. So that condition is used to make sure that R2 and RTD have to be the same. That into current square gives you the total heat that is being generated at the RTD. Now you find out that when
Sir,
there is,
I have a query over here. I'm sorry to
Yeah.
just, sir, this I value Vs divided by R2 plus 500, right, sir?
Yeah.
So let's say like from Vs, I current is flowing in the circuit.
Yeah.
So at the branch, in the upper half, there will be some current, and lower half, there will be some current.
Yeah.
Like I1 plus I can say like I will be getting distributed to I1 and I2. So let's say I1 is going through R1 resistance and I2 is going through R2 resistance, right? Sir?
Right. Right.
So, sir, basically this we are considering only like that means from RTD the current.
See, these two are basically symmetric. Okay. So
sense.
you will have the same current flowing through here and here. Okay. So
You
you
would say
basically can
both.
have R2 plus R3. If you divide that at the denominator and Vs, that will give you the current. Okay. Either you do R1 plus R4 or R2 plus R3, that will give you the current.
Okay, sir. Okay, sir. So since we'll finally assuming that this bridge will be balanced, hence it is like I by 2 in that sense, right, sir?
Exactly.
Right. Cool. Thank you, sir.
Okay. So you have the
Sir, why did we add R2 plus 500? Sorry.
so you have a potential of
Series
10
resistance.
volt is applied across this, right? So if you do not add resistance, how do you get the current? So either
Then
you do
basically
R1
it's
plus R4 or R2 plus R3.
series resistance, R2 plus R3. That's
Yes.
it.
Okay.
Okay.
I'm sorry, sir. I just intervened. I'm sorry for that.
Yes. So you basically calculate what is the temperature rise here because of this current that is flowing. Okay. So that is given by the resistive heating divided by the dissipation constant. And the resistive heating already you know from here, that you divide by the dissipation constant, that will give you the temperature rise. Now comes the interesting bit. So here this R2, which is same as the resistance of the RTD, is the reference resistance. Like this we write the formula, right, into 1 minus alpha times the reference temperature minus the temperature of this RTD. And this temperature of RTD is basically above the ambient temperature. So it is basically delta T. And this, when you substitute for delta T here, you get this equation. Okay. Now you are asked to find what should be the R2 value. Okay. Now this is a complicated equation. It's a complicated equation. So you cannot analytically find. You have to do some trial and error. Okay. So you can use a guess. Okay. Let's say the first guess was for R2 can be that R2 is at the ice point. Okay. So you can say that R2 is corresponding to 0 degrees centigrade. Okay. So you write that R2 corresponding to 0 degrees centigrade will be equal to R20 into 1 plus alpha into 0 minus 20. So you can see that I have written plus here, not minus, but I have changed. Instead of 20 minus 0, I have written 0 minus 20. So that will give me basically this is 500 into 1 minus 0.005 into 20. That will give me 450 ohm. So I start with a guess that R2 is corresponding to the ice point temperature. Okay. So when I write corresponding to the ice point temperature, my this delta T basically becomes 0. And so I have 500, which is R20 into 1 plus the ice point temperature minus 20. So or it becomes 1 minus 0.00520. That gives me 450 ohm. Now, this is a guess for the resistance. So what I do, this guess, I substitute on the right hand side, only in the right hand side. Then I determine this left hand side value. So when I do that, I can write R2 is 500 into 1 minus 0.005, 20 minus 10 divided by 450 plus 500 square into 450 divided by 0.03. So when I solve for this, I would get something like 454.2 ohm. Okay. Now, what I can do is now, so this is the first iteration. I can now put this value here on the right hand side, here, and I can find R2 2. So this will actually come out to very close to 450 ohm. So that means the resistance R2 is close to 454 ohm. Okay, so you basically, this is called Newton-Raphson method, but this is what we do. You start with a good guess. If your guess is not not appropriate, you have to do multiple iterations, larger number of iterations. But eventually, you see that for a guess value of R2, whatever you get R2 here, they should match. Okay. Now, once you know R2, you can now know what was the temperature error. This is because of the self-heating. So this delta T you can now determine by substituting for Vs, which is 10 volt, divided by R2, which is 454 plus 500 square into, this is 454 divided by 0.03. This will be close to 1.6 degrees centigrade. Okay.
Sir, I have a clarification to ask over here. Can I?
Yeah.
Sir, in this expression, R2 is equal to R21 minus alpha 20 into delta T, right, sir?
Yeah.
So this basically minus is coming because of because with the temperature the resistance increases, but minus is because we are comparing with ice point temperature, right, sir? We are
Yes.
going towards zero.
Exactly.
So, sir, if you're going towards zero, then let's say the temperature of the ambient is 20, which is which will be the like temperature of R2, because that is not at ice point temperature, right, sir?
See, basically what you do, okay, I have done a mistake here. So basically what you do is, this is the reference temperature. Okay. So you should write the reference temperature, resistance at the reference temperature into 1 plus the resistance temperature coefficient times the temperature at which you want to evaluate the resistance minus the reference temperature.
So basically
same thing only we're writing here.
Right, sir. So T0 will be 20 minus delta T, right, sir, if I'm not wrong.
Which one?
In this expression, RT is equal to R0, 1 plus alpha T minus T0. So this T is basically 20 minus delta T.
T is basically 20 degrees centigrade.
Okay.
Okay.
And T0 is, sir?
And your T0 is basically 20 degrees centigrade. So sorry, your T is basically delta T, and your
Right.
T0 is 20 degrees centigrade.
Right, sir.
T
Now
is
it's clear.
basically delta T. And T0 is 20 degrees centigrade. Okay.
Noted, sir. Thank you. And one more thing, sir. Suppose if the person is doing the like 454 ampere ohm that you have selected as a first gauge value, sir.
Yeah.
So that is, do you have any what I mean to say, sir, any shortcut
No, I mean,
shortcuts?
see, what we do is you have to guess for R2, right? So
Right,
one
sir.
immediate guess is that you say R2 corresponding to the 0 degree centigrade. Okay.
Ji, sir.
So you can see that when you say corresponding to 0 degree centigrade, your resistance is coming out to be 450 ohm. But it is not matching with what you actually get on the left hand side, right? So you keep iterating until you have a match. And when you have a match, you see that your delta T is coming out to be 1.6 degrees centigrade, not 0 degrees centigrade. Okay.
Okay, sir. Okay.
So that means basically, even if you wanted to maintain this at 0 degrees centigrade, you are actually having this RTD at 1.6 degrees centigrade because of the resistive heating effect. That's all it is telling.
Because self-heating.
Yes, because of self-heating. Okay, so I will stop here. We'll continue again some more questions from temperature measurement, mostly from the error in temperature measurement tomorrow.
Recording stopped.
And one more query, sir, I have, if you allow me to ask.
Yes.
Can I ask, sir?
Yes.
Sir, basically, in the while you're teaching us, there were a lot of derivations that you have taught us in that sense, right, sir? So will that be the part of the quiz? The derivation?
Okay. So that's what I was saying, right? I mean, if you want some clarification on certain part of the derivation that I have taught in the class, you
Yes, sir.
list those down. And if you tell me that these are the things that you want me to revisit, I would be happy to do that. But it will not be possible for me to tell you that whether I would include or exclude the derivation part. It is expected that you would learn the derivations, and I have already told you that it is going to be open notes.
Thank you so much, sir. No problem. Thank you so much.
Okay, so if no further question, then thank you all, and we will meet again Monday.
Thank you, sir. Good night.
Thank you.
Thank you, sir. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.